In this video, we will deep dive into the secret behind how transformers respond in real time. Imagine you're writing a sentence. After every single word, you forget everything you have written and reread the entire paragraph from scratch, word after word. That would be exhausting, and surprisingly, that's exactly how transformers would behave without KV cache. Today, I will show you why transformers are naturally inefficient, what KV cache actually stores, why it makes ChatGPT feel instant, and the memory trade-off nobody talks about. So let's dive in. Transformers generate text one token at a time. When generating the next token, the model must decide what in the previous context matters right now. That decision happens through self-attention. The core formula is a product of query, key, and value matrices. Every token produces a query, which means what I'm looking for, a key means how I should be matched, and a value means the actual information. Now here is the problem. When generating token number 1000, the model recomputes keys for tokens 1 to 999, the values for tokens 1 through 999, and then computes attention. Even though tokens 1 through 999 didn't change, that's like rereading the entire book every time you write one new sentence. Total computation explodes. Without optimization, generation cost scales roughly quadratically. So what's the smarter way? Here's the key observation. When generating token n plus 1, the previous keys and values are already correct. They don't change. They are already fixed. Only the new token needs fresh computation. So instead of recomputing everything, we store all previously computed keys and all previously computed values. In a memory buffer called KV cache. Now when generating a new token, we compute only the new query, the new key, and the new value. Then we append the new key and value to the cache and compute attention using new key and all cached keys. We reuse everything, no repetition. So without KV cache, in step 1 we will compute only one token, in step 2 we compute 2 tokens, in step 3 we compute 3 tokens, ... For step 1000 we're going to compute 1000 tokens. Without KV cache, each step computes just one token's projection. So instead of total cost growing like 1 plus 2 plus 3 all the way up to n, it simply grows like just n, linear instead of quadratic. In practice, this is 3 to 10 times faster generation. That's why AI chat feels responsive instead of sluggish. Here is the catch. We are storing for every layer, for every attention head, for every token, 2 tensors, one for key, one for value. So the memory grows linearly with batch size, layers, number of heads, sequence length, and the dimension of a head multiplied by 2. So for very large model, KV cache alone can consume tens of gigabytes. So speed is cheap, memory is not. So the real bottleneck shifts from compute toward the memory bandwidth. Researchers engineered clever tricks, one called multi-query attention, where keys and values are shared across all heads. Another one is called group query attention, where keys and values are shared across head groups. And the last one is page attention, which treats cache like a virtual memory, which is allocated dynamically. So frameworks like Hugging Face and VLLM and production inference engines handle this complexity automatically, but under the hood, it's still just the same idea: store old keys, store old values, and reuse them. And that's it. KV cache only works during inference. During training, we process full sequence in parallel. So caching doesn't help there. This is purely an inference optimization. KV cache isn't a new architecture. It isn't a new breakthrough model either. It's just a simple realization. Don't recompute what hasn't changed. And that's the tiny idea. What makes modern AI usable in real time. If you enjoy this deep dive into transformer internals, subscribe for more breakthroughs of how large language models actually work. Until then, see you next time.